This is questions number 9, 11, 12, 9, 10, 11, 12. Wow. And this is question number 9. So actually, I've gotten a lot of questions on this question before. I've answered this many times, and I think hopefully here I can kind of settle some confusion about this problem. So it says, two open flasks 1 and 2 contain different volumes of the same liquid. So different volumes, but we have the same liquid. Suppose that the pressure is measured at a point 10 centimeters below the surface of the liquid in each container. How will the pressures compare? So let's say I'm measuring the pressure here and I'm measuring the pressure here. And both of these are 10 centimeters below the surface. First note, what you'll notice is that this problem really only gives you that there's different volume, it's the same liquid, and we're measuring some kind of pressure 10 centimeters below the surface. It doesn't tell us which container has more volume. It doesn't tell us about the density of the same liquid or the liquid. It just tells us it's the same liquid and there's different volumes. But we do know that we're measuring the pressure 10 centimeters below. Well, what is the formula for pressure? Pressure, especially pressure due to fluids at a certain point within a container. And that equation is this: rho g h, where h is kind of like the depth. So h is not the height, it's the depth below the surface, and rho is the density, okay? So we know that they're the same liquid, so the density has to be the equal, correct? We know g is a constant, so that's equal. And h, well, we both know that these are both 10 centimeters below the surface of the liquid. So both equations, we would use 10 for h, or 0.1 meters. So because the height is the same, or quote unquote h is the same, or the depth is the same, g is a constant, it's the same, rho is the same, that means whatever value we get for this, even if we don't know the exact density of this liquid, we know pressure is going to be the exact same for both containers 1 and 2. So it doesn't matter if you have a swimming pool full of this liquid, or if you just have a straw, a very long straw with this liquid. Let's say I have a swimming pool, huge swimming pool, okay, filled with water in here, or filled with some kind of fluid in here. And let's say I have some kind of really narrow straw, okay? That is a terrible straw. And let's say they're both filled out by the exact same liquid. That means the density is always going to be the same, right? Density is an intrinsic property of a liquid, where density is equal to mass over volume. And it doesn't matter how much of a fluid I have, if the mass increases by a certain amount, the volume has to increase by a certain amount. Density is a constant for a fluid unless you change the fluid's state. So if we know density is always going to be the same, and we have some swimming pool with this fluid, and we have a straw with this fluid, if I measure the pressure at the exact same place, x meters below the surface, regardless of the shape of the container, it could be this trapezoidal shape, it could be a cylinder, it could be a swimming pool, it could be a straw, it doesn't matter. The pressure is always going to be exactly the same because this equation tells us that the pressure depends on the density, this constant, and that and the depth from the surface. So this seems a little counterintuitive, but just trust the equation. This equation tells you that the right answer here has to be A. The pressures will be equal. The next discrete here says, what is the identity of an atom that contains 6 protons and 8 neutrons? Guys, it doesn't get more straightforward than this. This is a very, very fundamental Gen Chem problem. 6 protons, 8 neutrons. You guys should know that the identity of an atom depends solely on the protons, okay? The number of neutrons will change what isotope of that atom is, but the identity of the atom itself only depends on the number of protons. So this could have said 1,000,000 neutrons or 1 neutron. Doesn't matter. The identity of the atom only depends on the fact that it has 6 protons. And you should know from the periodic table that the molecule with 6 protons is atom number 6, or element number 6, which is carbon. Again, the number of neutrons will change how heavy the atom is, and will therefore give its tell us what kind of isotope it is. But in terms of asking, hey, what is the element of this atom, you only know, or you only depend on the number of protons. All right, let's move on to the following 2 discretes. The first one says, which of the following substances is polar? All right, so there's 2 criteria that need to be fulfilled for a substance, I guess, to be polar. One, you have to have polar bonds. And number 2, well, not really in theme. Number 2, you need to make sure that the overall molecule is asymmetric with respect to these polar bonds. All right, so we'll go into that. So let's look at the first molecule, NF3. Actually, let's go over B, C, and D first. So CCl4. So it's always nice to draw these pictures. And Cl. This is exactly what this molecule would look like. Now, first, polar bonds. Is the CCl bond polar? Yes. The Cl molecule is more electronegative. So remember, polarity depends on electronegativity differences between the two atoms. The chlorine is definitely more electronegative than carbon, and so we have polarity, you know, going out towards the chlorines. Number two, is this molecule asymmetric? Unfortunately, no, it's not. This molecule is symmetric. So even though these bonds are polar, right? If you look at the vectors, the way these electron densities are, or these arrows, or these dipole moments are pointed, they actually all cancel each other out. So if you add up the vectors for these dipole moments, what will end up happening is you get a net zero vector. So there is no overall polarity in the molecule, even though the bonds are polar. So if you think about adding up this vector, and this vector, remember these are in 3D space, what actually ends up happening is these three down here, these vectors add up to a vector that goes downwards. And if you add up this vector and this vector, well, because they have the same magnitude but opposite directions, what ends up happening is they cancel each other out and you end up with a zero vector. And so since this molecule, even though it has polar bonds, is symmetric, this bond is nonpolar. Or this molecule, this substance is nonpolar. Now let's look at CO2. This is the structure of CO2. Again, oxygen, very electronegative, carbon not so much, so the dipole moments point towards the oxygens. However, because this molecule is symmetric, right, these two vectors will cancel each other out and give it a zero vector, and again, this molecule will be nonpolar, even though it has polar bonds. Now, Li, unfortunately, there is no polar bond here, right? These are two symmetric or exactly the same molecules, so they have the exact same electronegativities. There is no polarity between these two, so there is no electronegativity difference. There is no polar bond. This is not a polar bond, especially since you have the exact same molecules, or the exact same atoms here, exact same elements. And so it doesn't really matter if this is symmetric or not. We already know that we fail criteria 1 since there are no polar bonds, given that these are two exactly the same atoms. So NF3, let's look at NF3. I'm going to move over to the right here. There's a nitrogen, fluorine, another fluorine. All right, so is the NF bond? Is the NF bond polar? Yes, it is. Fluorine, super electronegative. So you're going to have these dipole moments pointing out. Now, because this molecule is asymmetric, okay, the lone pairs do not contribute to any dipole moment, at least, in this case, in the simple case. What ends up happening is these two vectors, they do not cancel out, and when you add them up, they actually point downwards. So since there is a net dipole moment, this molecule, or this substance, is polar, and we checked out the two criteria. Number one, polar bonds, and then we check to make sure that this is not symmetric. We know this is asymmetric. These vectors do not cancel each other out, so we know they're for a fact asymmetric. So we know for a fact that this molecule has to be polar. So A is the correct answer. Let's move on here. If all else is held constant, which of the following changes would not double the volume of a gas? All right, let's go through B, C, and D again. Let's look at B, doubling the absolute pressure or absolute temperature. All right. This is the ideal gas law. Now, if everything else is held constant, this is the same, and we know R is always constant. If we double the temperature, right, we're going to have to double the volume in order for this equation to hold. So if temperature, let's say like 10 Kelvin, and we make it 20 Kelvin, then since we doubled the right-hand side, we have to double this left-hand side. And we know that pressure has to be a constant, so we have to double volume. So this would doubling temperature would double volume for answer choice B. And we're looking for something that would not double the volume of the gas. All right, so let's look at having the pressure. Well, if everything else is constant, this has to be constant, this has to be constant. Well, R is always a constant. And number of moles of the gas molecules is constant. If we have the pressure by 1/2, then we have to double the volume in order to make sure that everything else is the same. So for example, let's say pressure was 500 and volume was like 500. if we have pressure to 250, well, then we need to double the volume to 1000 in order to make sure that the right-hand side of the equation is still equal to what it was before. 1/2 P times 2V still has to equal nRT, and we see that it does, right? 1/2 and 2 cancel out, so PV equals nRT. That's why we double the volume when we have the pressure. So we know this, having the pressure will double the volume, so C is wrong. Doubling the number of gas molecules. Same thing here. It's saying, hey, what happens if we double N? Well, everything else has to be constant. So that means if we put 2N R times T, then there has to be 2, double the left side as well. And if pressure is constant, then the only thing we can really double is volume. So that's a P times 2V. And so again, we know that doubling the number of gas molecules will double the volume as well. Finally, doubling the pressure. What happens there? This is constant, this is constant, this is constant. If we double pressure, we get 2P. Well, if we want to make sure that this is still equivalent, this is still the same number, it's the right-hand side is still a constant, we would actually need to have the volume here, right? So, because then we would get 1/2 and 2, these cancel out, and finally we get the original expression PV equals nRT. So instead of doubling the volume, we would actually have to have the volume if we want to double the pressure. So this would not double. Doubling the pressure would not double the volume of the gas. And remember, this relates to Boyle's law. PV, P1 V1 equals P2 V2. Basically what this means is P1 times V1 has to equal some constant C. And another way to think about this is if I double the pressure P, to make sure that this value stays or remains a constant, I need to 1/2 the value of V1 in order to make sure that we're still, again, looking at a constant value. So again, doubling the pressure through Boyle's law, not just the ideal gas law, but through Boyle's law, doubling the pressure would have to half the volume of the gas as opposed to doubling the volume of the gas, making, again, A the correct answer. Just as a side note, PV equals nRT, the ideal gas law, that is a combination of all of these mini laws like the Boyle's law, Charles's law, things like that. So just know that the ideal gas law is an amalgamation of all of those other preliminary laws or relationships.